Good afternoon, sir.
What's up? How are you?
Fine. At 1 o'clock, the voice is okay. Wait,
You have got some
please,
problem with your
still.
sound. I can't hear you. Maybe you can try by rejoining.
Good afternoon. Join through mobile now.
Yeah, I mean, I can hear now.
Yeah. So 1 week gets over today.
Yeah, that's right.
And sir, I'll be conducting my end of the lectures Saturday and Sunday.
Okay, that's fine.
Yeah. And Saidulu sir is going to take one lecture tomorrow.
Okay, okay. So what's the topics? I mean, you are covering Saidulu and you?
Saidulu sir is actually going for research initiatives
Okay.
in renewables.
Okay,
And
okay.
I am taking. Hello. Yeah.
Yeah,
So
I mean, I could not hear you, but
yeah,
I can hear now.
yeah. He is going to take research initiatives in renewables,
Okay.
and I'm going for economics, renewable economics, costing.
Okay, okay.
And Sunday, I'm planning to take a tutorial on management, energy management.
Okay, okay. Is it like problem solving tutorial or is like
Yeah.
no?
No, problem solving.
Okay. So how you are planning to run problem solving? Is it like you'll just explain or you?
Yeah. Initially, I'm planning to explain the fundamental. Then I'm planning to ask them to develop the algorithm or
Okay.
flowchart and do one hand calculation if possible.
That will be online as well, right?
Yes. And data I will provide. The initial data. Yeah, Gagan, can you give us a feedback as to how you are feeling as to how the things are going?
I mean, from my side or from attendee side?
Attendee side, I'm asking. Gagan,
Yeah.
if you can, or Vishnu, is it?
Yes.
Good
Hello.
afternoon, sir. Hello.
I just wanted to know how the things are going. What do you think?
Yeah, it's good. And you are also shared that PPT that is helping more. Yeah. We can go through it after the classes. So I think that is fine.
Vishnu, can you introduce yourself also?
Yeah, my name is Vishnu Charan. Actually, I am working in Tata Projects, and basically I am into the design side, engineering side, and I used to design for all power plants and switchyards and all. I have total 18 years of experience in industry, And presently we are focusing on the fuel cells, that is a green hydrogen concepts we are doing it. That is the reason I registered this particular course. It is more interesting in the storage energies and all.
Yeah, I mean, we haven't started green hydrogen
Yeah,
as well. That will
understood.
be
Yes,
next
sir.
week. But what part of the green hydrogen you are working or you're thinking to work?
Actually, we are executing some of the projects and tenders. We are involving it, like NTPC in India. They are coming up with like green hydrogen and then pumping back with fuel cell. They are pumping back to the grid. That 25 kilowatt. They are doing prototype now.
Okay.
So that part is involved, and also the most of the ONGC and oil and gas sectors for refinery, they are using this hydrogen. Now they want to generate this hydrogen with green energy.
Okay.
Yeah.
Yeah. I mean, we'll also discuss, I mean, those sort of things. Most probably when we'll be talking about hydrogen on
Yes, sir. Yeah. I'm eagerly waiting for that actually.
Tuesday. Most
Yeah.
probably that will be on Tuesday.
Okay. Thank you.
Yeah, most welcome.
Gagan, can you introduce yourself?
Yes, good afternoon, sir. I'm Gagan Menon. I'm doing my PhD. I have recently joined the PhD program in Electrical Engineering Department at IIT Bombay.
Okay.
Under whom? Who's your guide?
And under Professor Soman, S.S. Soman.
Okay. I mean, I met once, there is a female professor, I forgot her name, but she was doing research in electrical power, but I forgot her name. Is there any female professor, I mean, in your in power system group in IIT Bombay?
Yes, sir, Professor Anupama Kohli.
Yeah. I met her once.
We actually have two students from Professor Soman now.
Okay.
So I'm willing to work in the area of this optimal storage for a given renewable mix.
Okay.
So
So
that's why I joined this course to learn about the modeling of different storage systems and how to integrate the renewables with the storage.
so you mean mainly that optimization sizing or like the grid, finding the grid like voltage frequency as well, or just like the optimization and modeling?
So first of all, modeling and optimization, and then after that evaluating the performance of the renewable and with storage integration into the grid. So both will be there.
Okay, that's great.
Thank you, sir.
Hey, Ibrahim, welcome.
Oh yeah.
Fine. How about you?
Yeah, everything's fine. Good thinking.
Ibrahim, you want to go first or you just joining?
I'm just joining, so I think it's better if you're gonna go through the presentation because the administration will be related to that. Yeah.
No, that's I already did yesterday.
Okay. It's up to you. I'm happy to start if you would like to start, and then me, as you like.
Because the one that I'll be doing. That's on mostly electric vehicle.
Yeah.
But I mean, if you prefer, I mean, you can do it, no problem. But if you prefer, you know,
I'm happy with both with either, like whatever suits you. I'm happy with it.
then you can do it, and then you can leave.
Okay, no worries.
And then I can continue.
That's totally fine. So just I'm gonna just get the paper related to that code, just to show some examples. Just give me a moment.
So is it Altab okay or?
Yes. Whatever you feel is better.
I think that's because we already have discussed. So
Give me a moment. I'll be ready. So let me start then.
so please go slowly, so that you know people can.
Yeah. So just let me download this paper, which the code's related to this paper, so then I can show them the output and the input, because it's time consuming to run the code and waiting until the optimization done. Or
Hi everyone. So welcome again. So this is our 5th day. So today, I mean, what we are doing, I mean, Ibrahim is just going to show an example of how you can apply, like, AI, mainly for photovoltaic system, as well as, battery sizing application. And this is for a standalone photovoltaic system, the example that I have shown yesterday. So Ibrahim will try to go slowly, but please feel free to ask any question or comments that you have while Ibrahim will be showing the demonstration.
yeah, so thank you, Dr. Jangir. Thank you, everyone. So the first thing is the
Can you make it a little bit bigger or?
Oh, okay. So that's why I was trying to ask about. That's fine. Let me just double check if I can do that. I believe there is a comment. Maybe
There in view, I think so. No.
the view is mostly for the Windows.
Arpita, can you tell us?
Sorry?
No, Arpita, actually, they have been doing it recently. Presentation of coding. Maybe
Yeah.
she is very.
Yes, sir. Preferences we have to go in order to increase the font.
Where's that?
I think home. Please go to home.
And then preferences. Yeah.
Yeah, preferences, and then
The font.
I think it's fonts. Yeah.
Yeah.
Increase it to around 16 or something.
Say 18.
18. Yeah, that would be great.
Yeah, I think it's working. Yeah.
Maybe 18 is too big. Now it's better.
Yeah.
Okay. Cool. So the thing that I'm gonna just explain. So please stop me whenever you have a question. So, like Professor Jahangir already yesterday showed you an example of the development of a standalone BV battery system. So it's already a published paper, and that code actually related to this research work. So the point of doing this system is to power, like for powering a mobile network base station. So we have, you know, that mobile stations or towers, sometimes they are in the mountains or they are a little bit far from the from the electrical grid. So because of that, mostly they use diesel generator to power these stations. Or let's say that we have a rural house or area, and that stage we need to add BVs or batteries. Let's say you have a farm a little bit away from the city, from the electrical grid, then you need to power that using renewable energy resources. So one of the options is photovoltaics, but because at night we don't have sun, then we need storage systems to store the excess energy that will be generated from the photovoltaics, and then we're gonna use it at night to power the system. So if we just have a quick look to the PV system, it's already explained for you guys that there is a several way to model the PV. One of that is the mathematical. So once you have a huge amount of data, and that's a small amount of data as well, the high resolution, the mathematical representation sometimes is not accurate enough to do the optimization and do the modeling. So one of the techniques that you may use, machine learning or deep learning algorithms. The main idea of the deep learning or machine learning, so you have an actual data for the meteorological variables like the solar radiation, ambient temperature, also the pressure, wind speed. And you have also an accurate or actual performance data as an output from the PV, like the current, the power, and the voltage. So the mathematical equation, you can use it if you don't have these values. But once you have the input and the output, so to model that, you may use machine learning or deep learning algorithms. So deep learning is more accurate because it has several layers. Let's say artificial neural network, it has one layer. Deep learning has several layers. So once you do the training and testing, so there is a high accurate results you will get it comparing with artificial neural network or other classical machine learning techniques. Again, so the mathematical equation may have some assumptions, but once you have actual data for actual PV module, then modeling that using the mathematical equation may not give you the accurate results. So that's why in this paper, because we have the actual data as inputs, actual data as output, then we used deep learning algorithm. So this is an example of the system that we have. We have PV array, we have storage battery, and we have a load. So we need to find what's the optimal size for the PV, what's the optimal size of the storage battery or the capacity of the battery that can actually support the load with a minimum loss of load probability, which is the amount that the power of these two sources like not able to meet the load demand, okay? So I think that's what I just give you a general idea about that. So the first code that I'm gonna showing you now, it's the model of the PV using a deep learning algorithm called LSTM, long short-term memory. So because we're gonna predict the output current, in our case, we use the current as a factor or as an impact factor to do the modeling and optimization, okay? So because we wanna predict the output current, so the most important two inputs affecting the output current of the PV, the solar radiation and also the temperature. So I'm just gonna give you a quick idea about the data that we use. So we have here the month. The month one means January, goes down to the other months. So this is a full data for 1 year. based on hourly basis. We have the day of the year, which day. So that means the 1st of January. And then the hour. So we started our data from the 4 a.m. and goes down to 7 p.m. because after that, there is no solar radiation. We have here the solar radiation, which is the global horizontal solar radiation. We have also the ambient temperature. We used also the pressure, wind speed, wind direction, humidity, and also the PV temperature. So the temperature of the cell or the module, it's different than the ambient temperature. So we used the both temperature to see the correlation between these. And the output of this model, like this data, we can see we have an actual data for the BMP, which is the power, the maximum power point, the current at the maximum power point, the voltage at the maximum power point, also the short circuit and open circuit. But because we're going to use just the current in our optimization, because it's standalone, it's not connected to the grid to study the voltage and other things. So in this case, we use just the output current at the maximum power point, IMBP, as the output of the LSTM. So from column A to J, these are the inputs, and column M is just the output. So we know in the machine learning, deep learning, we have to use like a part of the data for training and the other part for testing and validation. So this is the full data, and then we divided the data for training and testing. So 70% of the data went for training and 30% of the data went for validation and testing. So how are we going to build the code for that? So I believe that most of you guys know how to use MATLAB. So the first thing, we use these three functions. The main idea of this just to clear the workspace, just to make sure that if I was working in MATLAB before and something saved in the workspace and has the same name of one of the like parameters or the functions or the variables that I'm going to store, that we may do some conflict. So that's why it's preferable to use a clear and a close all to clear everything from the previous session and close all like the figures and all of that, just to make sure that you're gonna write your code from scratch. So after that, we actually imported the training data. So we have X train and Y train. So X train means the input training data, which is, as I mentioned, solar radiation, ambient temperature, pressure, wind speed, wind direction, etc. And the Y training in this case, as you can see, is just for one column, which is the current at maximum power point. So here we used XLSRead function. So that's a function, you can use it to read from an Excel sheet. And then you write the name of that Excel sheet or the Excel file, and then the name of the sheet. So if we just back here, we have down, as you can see, this is the file, and we have several sheets, full data, training, testing, visualization in the bottom of the file. So also we called in the training, we go the training, in the testing, we're gonna go with the testing name of that sheet. So we go the training, and then we defined the number of cells represents the inputs. So the training, so this represents 70% of all of the data, and X-train represents a 30% of that data. We did the same thing for testing, use the same function, and then we got again 70% of the output, which is the current at maximum power point, as an X test, and the Y test, the remaining 30. So we're gonna use the X, like the training data as an X train, Y train to develop the model, and then we're gonna use X test, feed it into the developed model to predict the output current and compare it with the actual Y test to see the performance or the efficiency of our model. So this is this part actually, and the part underneath. So because we have another code, so I'm gonna go quickly into that, just focus on the main parts. So this part here, we just did some cleaning. You may find some of the data are negative. So we just did some cleaning to remove the data. So especially in the training, so we don't have any temperature any solar radiation negative or any current as a negative current. So that might be some error in the data. So these codes here, we just make sure that our data is clean and it's ready to be used. So this one, the first one for X train, the second one for Y train. We did the same thing for X test and also Y test. So the second thing is, once I prepared the data, imported the data to the MATLAB, and also I cleaned the data, then I have to start building the LSTM architecture. So I'm gonna build that because LSTM contains several layers, hidden layers as well. I wanna also make sure how many inputs I have, how many outputs I have. So I have to build the architecture of the LSTM before start the training. So there is in MATLAB actually already a built-in function for LSTM. So guys, you can write doc, and then, for example, we have LSTM layer. I don't know if you know that. If you write in the command window doc, which is from document or help, and then just write, for example, we're looking for LSTM layer, and then if we print, press enter on that, we will get some MATLAB documentation. So because it's already a built-in function, so you will know what exactly the syntax for LSTM, and there is also description and how you're gonna use it, what's the hidden in your units inside it, and the format. So the good thing with MATLAB, you have full documentation for each function built inside the MATLAB itself. So in this, actually, we just use LSTM because it's one of the well-known and the most used deep learning algorithms. So what we did actually, because we have 9 inputs based on the Excel file, so we decided that the input size is 9. Because we're gonna predict just the output current from the PV, so we use the number of response as 1. So the default number of the hidden units inside each layer in the LSTM, it's 200, so we kept it 200 without any changing. And after we defined these inputs for the LSTM, we start building the architecture for the LSTM. So because we have layers comparing with the normal or classical artificial neural network, so we used something called sequence input layer. So that sequence input layer will define or will be connected with the other layers based on the inputs, which is 9 inputs. So also we have an LSTM layer, the main layer. This main layer will contain 200 hidden neurons inside it. So this number, like the 200, you can change it. You can make it higher or lower. And this is another actually research question, which is how many hidden units should be mentioned in my problem. So this is a default number. You may do some optimization for that to know what exactly the optimal number of the hidden units. In this study, we did not went through that detail to study the number or the optimal number of hidden neurons. So after that, we also use the full connected layer. So we're gonna connect all the layers together because each layer represents classical or normal artificial neural network. So we have to connect all of these layers to give us one output. So the first thing we decided that this is a sequence input layer. So we have several layers, and all of them, they have 9 inputs, and then we connected all the layers at the end to give us one output, which is the current. Because we're doing a prediction, not a classification, so that's why we have to define that this is a regression layer. If we're gonna do classification, then that will be a classification layer. And after that, there's another important thing which we called it the maximum epochs. The maximum epochs, like in each iteration, the inside the LSTM itself, as I mentioned before, that why we're using high data or high amount of data, because we want to make sure that once we're building or train the LSTM model or artificial neural network or any machine learning algorithm, there is some weights start calculated between all of these neurons to give us the highest accurate output. So based on that, we should do some optimization inside the machine learning or deep learning algorithm, which is the good thing in the LSTM. This optimization done inside the LSTM itself. So how many times I need to optimize these weights in each run for each hour? So here we decided we need to do 1,000. Again, you can change it. So 1,000 may take more time, but it will give you more accurate value. You may make it 10,000, 100,000, or maybe 10. Again, this is another question. What is the optimal number of that? And also you can also later take that as a research idea and do some optimization to find the optimal number of epochs to do the prediction. So the second thing is, after we define the layers structure, we need to define some options inside this layer. As I mentioned in the training, there is an optimization technique inside the LSTM, and that will optimize the weights to reduce the error to give us the high accurate output. So how are we gonna decide what is the optimization inside? Again, the LSTM, it's built in. And what is the threshold, the learning rate, what is the drop period, the drop factor, and all of that. So we have to use a function for LSTM called options. So in that, we give the function called Adam. So that function actually is used as an optimization to optimize the weights and reducing the error inside LSTM itself. Again, this is a built-in function. So the maximum epochs for the optimization for each run is 1,000, which we defined before. The threshold, it's 0.01. Initial rate, we start from 0.01, and then we start reducing that. So all of these actually learning rate schedule, it's called piecewise. There is other learning rate. Once you do the doc for LSTM, you will understand what's this meaning. And what's the meaning of that, and what's the other options for that. The same thing for learning rate drop period and the learn rate drop factor. Like once I do each optimization, what's the delta, let's say AMP, for example. So for example, 0.2, that will be the drop rate factor to start reducing or increasing the weights inside the LSTM or neural network to improve the output. So there is another thing, which is just the plot. So the plots here plots the training process or the progress. We can see, if we use that plots function, so once we run the code, we will see how the LSTM start reducing the error to improve the accuracy. We can visualize that as well. So before jump to the training, anyone has any question into the architecture design, importing the data or cleaning the data? Any question? Okay. So once we developed the LSTM, we imported the data, cleaned the data. So now we need to train that architecture that we developed for the LSTM. So to train the data, we can use a function called train network, and that will use XTrain, which is the XTrain data that we imported, and the YTrain data, which is the output, the current in this case, the layers, that the architecture of the LSTM, and also the options that we defined. We need the LSTM behave using these options to give us the high accurate results. So here we're using a function called tick. The tick and took, these functions, you can use it to measure simulation time for your code, when that started and when that's end. So you know how long that code took to do the training and testing. So for training, we use tick, and then we call the train time took. So while like LSTM is a train itself, we will measure the starting and the ending point to know how long the training period took to give us the training model. So once you train the model, now we're gonna test the model. So we use a function called predict using net. Net represents the trained model that we already trained, and it's ready now to predict our output. So we feed the XTrain, which is the 30% of the full data, only the input. we use that with the trained model to get the output, which we called it Y predict, and then we're gonna compare it with the actual output that we have to make sure that the predicted value is like the accuracy of that predicted value. We're gonna do some statistical error calculations like root mean squared error, mean absolute percentage error, and all of that, just to make sure that our model is developed well and the output satisfying comparing with the actual data. So we use that to predict, and we save the predicted data in an array we call it Y predict. So again, here we just make sure that everything is fine, and we clean the predicted data as we did in cleaning of the training and testing data. And after that, we did calculate the mean bias error and also the mean absolute percentage error and the root mean squared error. So based on this, we will also do two figures. The first figure represents the output current and the actual current, and the second figure shows us the normalized root mean square error. So if we just back to the paper, in the result side, so this is the figure that we will get from that code. So the orange one or the red is the predicted after we trained our model. So that's the prediction value. The observed, the blue one, which is the actual 30% output that we kept it for validation. And once we compare these two together, we will get the root mean squared error or the normalized root mean squared error, which is an error figure, shows the error comparing between these two. As we can see, it's in a percentage like less than or around 1%, which is almost we can neglect that. So that means our model developed well, and the output from this model, we can use it now to do the optimization to optimize the size of the PV and the battery system as well. Any question before I go to the optimization code? No questions? Okay. So let me just close that. Okay. So if we just back a little bit to the figure that we have to show exactly, because if for any optimization problem, you have to understand that problem to be able to write to develop the model and also to find the objective function and how you're going to link the battery with the PV and the load. So if we just have a quick look to that figure, I think it's here. Yeah, here. So what will happen from this figure? So we have a load, and this load needs some current that should be consumed within the time, and we need to find or to meet this demand as a current from the PV and the battery. So that means, for example, if we don't have a battery, we're gonna get some output current from the PV array, and then we will see, is that current equals to the load or not? If it equals, all the current will go to the load. If not equals, that means we need more current to support the load, and that should come from the grid or from some other source, which is the battery in this case. Let's consider that the output current from the PV system is more than the load current. So that means a portion of that current will go to the load, and the extra current that we have, which is we call it excess energy, excess current, we're gonna store it somewhere or we're gonna damp it. If we don't have a storage system, we're gonna damp that. If we connect that to the grid, we will sell the extra to the grid. Otherwise, because it's a standalone, so there is no grid in this case, so we have a storage battery and we're gonna save the excess energy here. So how are we gonna build this current flow between the PV, between the battery, and between the load? And this is one thing that we have to think about it. And the second thing, because it's a project, so the customer, he cares or she cares about the money as well. So I can solve this problem with 100 batteries and 100 BVs. That will solve the problem, but that will need a lot of money to spend it to build that system. So I have to think not just about the technical solution and also the economic, the most economic solution, the minimum cost that the customer will pay to build this project. So in this case, the optimization that I'm gonna do to find the optimal number of PV modules and the optimal capacity of the battery, I have to consider two factors. The first one, the technical, which is, as I mentioned before, the loss of load probability, which is the amount that the PV system and battery can or cannot meet the load for the current in the load. The second thing is the economics, the money. So as I have two options, two things, or two factors, I have two options to solve this problem. The first thing, using a single objective function for the technical. After I found the several options, I can use another single objective function for the economic. Or the second option, which we're going to explain, which is a multi-objective function. That means I can use the both functions together in the optimization for one time, so I can spend less time to find the solution. At the same time, I'll get the answer directly from this optimization. So what we did in that, so the most important thing, as I mentioned, we have the current of the load and we have the current of the PV. Based the current of the PV, we predict that current in the LSTM model. I just explained it before. And this is actually, as you can see here, I have several currents. I have here the hour. I have the actual current, which is the actual current. We know that someone measured that actual current from a real PV system. This is the output current from the simple model, which is the mathematical equation. As you can see that, for example, here 0.17, 0.18, and all of that. So we have the artificial neural network, we have LSTM model, and also we have the load demand. So in this actually study, we are interested to use LSTM model and load demand. Because it's for research purpose, we have to do some validation. So that's why we used also artificial neural network, the current produced from artificial neural network and also from the mathematical equation, just to do validation to show that LSTM model is more accurate than these two. So this load demand, it's the current that the load will consume. So we need to meet this load demand through the PV to find the optimal size for the PV and also from the batteries. So what we did here again, we used the clear just to make sure that we cleared the workspace from the previous LSTM model. And then we actually use XLSRead to read the current for the load, which is the load demand. And also, as you can see here, we have three functions, but all of them commented. So we use that for LSTM, artificial neural network, and simple. But here, as we use the comment, so that means now we just use that. If there is a comment before the function or before the line code, that means the MATLAB will not read that. So in this example, we just read the load current and also the PV current that is produced by LSTM. And that IPV, it's for one PV module. So we may need to add more PV modules to meet the load demand, or we may combine that with the batteries. So again, here we did not use TikTok. We use a CPU time, but because it's this optimization needs maybe 4 or 5 hours to do the job. So CPU time will be more accurate in this case to calculate the optimization time that the MATLAB needs to do the calculation. So the first thing, actually, we saved the current of the load, the current of the PV in a file, M file, or mat file, sorry, in MATLAB, and we called it var fitness function. So that actually multi-objective window-driven optimization, okay? So for this function, we use the current in the PV that generated and the load current because we're gonna use it in the objective function. So the objective function will contain the current flow between the PV, battery, and the load, as well as calculation of the loss load probability, the technical factor, and also the economic factor. So before doing that, we defined some of the PV and inverter characteristics, as well as for the battery and some specification, like the PV efficiency, the wire efficiency, inverter efficiency, the voltage of the system. For example, here we consider it single phase 230 volt. The peak sunshine hour is 5.5 as an example. For that location, the voltage of the battery, we consider it as a 12 volt. You can use 48, you can use other voltages based on the market, but in our case, we use the 12 volt. The discharge efficiency, the depth of discharge, like the amount that we can discharge the battery without harming the battery, it's 80%. Alpha, which is like Dr. Jangi explained that before, alpha related to the ratio between the current and the temperature. We need to consider the temperature effect on the current that we're going to predict. So the PV array per watt peak, it's 300. So each PV module produce 300 watt. Okay. So once we do the optimization, so what we exactly doing in optimization, we gonna give the optimizer several solutions. So let's say from 0 to infinity, there is solutions. One battery, 100 BVs, 100 or 2 BVs with 200 batteries, for example. All of these solutions, from 0 to infinity, we can find solutions. But the optimizer cannot go from 0 to infinity because it will diverge, it will not converge. So that's why we have to define lower limit and upper limit and let the optimizer start searching between these limits to find where exactly the optimal value. So we need two limits, one for the PV and another limit for the battery. Okay. So to do that, actually, we firstly we used an intuitive method. This intuitive method, we use it just to define the maximum limit. So we know the minimum limit is 1 PV, 1 battery, or 1 PV, sorry, 0 battery. So we have 0 as a beginning, but that might make some issues. So we started from 1. So we have 1 PV, 1 battery, and that will goes up to a maximum limit. So to find that maximum limit, we use intuitive method. So here an explanation how we did that. So we firstly find the power of the load. We have the current multiplied by 230, which is the volt, with impact factor that an assumption 0.95. We know the area of the PV, which is 1.64 as a length meter with 1 meter as a width. And then we find the energy of the load. To find the number of the PV module, using the intuitive method, we used this equation. So the minimum PV, as I mentioned, 1 PV, and the maximum will be that one that we calculated. The intuitive method from the literature make an oversized assumption. So that means it might consider that the size for, or the number of the PV modules, 20, but the actual one might be 15. So it's oversized because of the safety factors. So that's why we used it to find the limits. So the minimum limit is 1 PV, the maximum limit is in PV, which we calculated from from this equation. The same thing for the battery. We used the depth of its charge, also the discharge efficiency, and we use the NH, which is the cloud that could be in the system. And from that, actually, we started with the C minimum of the battery, which 1,920 ampere hour. And the same thing, we found the maximum to be the one that we calculated from then. So this is for one battery, and then we calculate the maximum one for using the intuitive method, which I mentioned before, it's over optimized. So doing that, we defined the minimum and maximum limits for the PV, minimum and maximum limits for the battery, and we put it in the DEM minimum, DEM maximum. So this is for PV low, battery low, and the dimension maximum, PV high, battery high. Okay. So now we imported the data and we defined the limits. We defined the specification for the PV, the battery. We defined also the limits for the optimization, the minimum and the maximum for the PV and the battery. So at this stage, we are now ready to use the optimizer to start optimizing our job. So before doing the optimizer knows I have to try something, but how can I try that? What's the relation that I have to put these different limits inside it, which is the current flow. So before going to the current flow, I'm just gonna go through some definition of the parameters for the multi-objective window-driven optimization. So the parameter size is 20 because we have two things, two unknown values. The number of the BVs, the capacity of the battery, so two things. So the population size mostly is the number of the unknown parameters multiplied by 10. As we have 2 multiplied by 10, we have 20. We have two parameters, which is unknown, again, number of BV, capacity of the battery. And then we have something called maximum number of iterations. So in the literature, it's recommended to use 500 iterations. So that means the optimizer will try 500 times to find the optimal location. Every time giving some values from the limit, throw it into the current flow model that we're gonna build, and then give us the output and see is that the optimal or not. So how it will decide based on minimizing the two objective function I just explained, the loss of load probability and the economic factor, which is the annual total life cycle cost. So by minimizing these two, every time they will, like the first iteration, try, let's say 5 BV and 2 batteries. And then they will find the amount of the loss load probability, the annual total life cycle cost. Because it's multi-objective, they will find a factor can summarize these two together. Let's say that that output was 1. The second iteration, try 3 batteries, 5 BVs. That value is 0.9, which is less than 1. So then this is the optimal values now, the second option. The third iteration, it will try another thing, fourth iteration. So every time it will try new values until it couldn't minimize the summation less than the amount that got from the previous iteration. Let's say we got 0.5. So this is the minimum. The MATLAB tried different times to solve it by the optimizer. It couldn't find any objective function less than this amount. That means it's converged. So to make sure that it will converge within the time with trying all the options, we gave 500 iteration as a maximum number of iterations. So this actually CMAEC algorithm is something related to the algorithm itself. So there is each algorithm or each optimization technique, it has some hyperparameters. So the good thing with the multi-objective window-driven optimization, these hyperparameters, it will be updated with time internally. As I explained in LSTM, they have internal optimizer. Also, this optimization technique, it has also internal optimizer to optimize the hyperparameters inside the optimization itself to improve the output or the accuracy. So here we initialize the multi-objective window-driven optimization. We gave a position and velocity. So this is equation already needs to define the position and velocity. What I mean by that, for example, let me just get a paint. So what's the meaning of the position? Let's say that this is the search space for the BV and batteries, okay? So the solution could be inside this. So by defining the minimum and maximum limits, we define these limits. As an example, it's a circle. So the solution could be anywhere, could be here. Sorry. The solution could be here, could be here, could be in the edge, could be in the middle. So we have to define firstly a position as an initial position that the optimization will start to do it. So let's say, I'm just gonna explain quickly how the optimization artificial intelligence techniques works. So let's say the solution is here, okay? So this is the solution, okay? And then I'm gonna just define initial position here. So this is the initial position, okay? So the optimization technique, the artificial intelligence techniques, if I compare it with iteration algorithms or iteration optimization techniques or iterative, they're gonna search or try all the options inside these limits to find this one. So that's why it needs more time. It's more accurate, but it needs like like more time to find the solution. If the AI needs 2 hours, that may need 1 day to do all of the like searching all of the searching space and do all of the optimization inside it. So what's the AI doing exactly? Artificial intelligence techniques. So for example, if we just defined one solution, just move that. So if we just start using, I'm going to use the, yeah, let's use that. So we defined as an initial position here. So this point means, for example, 2 batteries, 2 BVs as an initial value. So this value of the optimization technique will take it and put it inside the current flow model for the BV battery and the load and see the output, which is the objective functions. Let's say the minimum objective function is 0.01, okay? Let's say 0.01, for example, okay? So we have to minimize that to find that value or something less to say that this is the optimal value. So for example, the objective function in this point is 0.01. So what's the MATLAB doing? It will define a limit, a small limit by itself, and search between this one. And after they use that option, they will test to see the optimization value for the objective function. Is it more or less than 0.01? If it's more, that means the output somewhere else. So that means we're gonna now use this as the first limit, and this is the second limit here. And again, it will start searching here. So if it's lower than the previous one, that means the solution in this direction. If it's more than the previous one, so that means the solution in the other direction. So in our case, the solution in this direction. So as it's lower than the previous value, but still more than the threshold, in this case, the AI will again use this as a one limit, and then let's say they use this one as another limit and search. Again, if the value that we got from here less than the previous one, but still more than this one, so the solution in this direction until they found this solution. So once they found this solution, they will stay searching around to see if there's any value else less than this. If they couldn't, then the optimizer, the artificial intelligence technique as an optimization technique will tell you this is the minimum value I got. This is the optimal solution. So we use 500, as I explained, just to make sure that the AI or the optimizer will try to find all the solution around, not just stuck here without finding other solution, okay? So that's the main idea of the optimization technique. So that's why we give it an initial position, initial velocity. The velocity is how fast this, like let's say search will jump to another step, okay? So in each time for this position and this velocity, as I mentioned, we will use the position exactly, like especially the position, to check the optimization or the objective function. So what we did here, we defined based on the dim max, dim minimum, which we defined before, the minimum and the maximum limits for the BV and battery, to give that, to add the position to them, to let them between the 2 lines I just explained in the paint, the 2 lines, with the position where exactly fit between these two lines. And then this position will take it. The position represents number of BV, number of batteries. We will take that position, which here represents X, and throw it in the fitness function to find the summation of the 2 objective functions, loss load probability and the annual total life cycle cost. So what's inside this fitness function? Inside this fitness function is the current flow of the model. So if we go to the fitness function, so because of the time limit, I'm not going to go in detail, but just a very quick explanation. So here we loaded the var fitness function for the multi-objective one-driven optimization, the current of the BV and the current of the load. If you remember, we saved that at the beginning here.
Ibrahim, I mean, you don't have to jump. I mean, if you need extra time, it's fine.
Okay, that's fine.
Yeah.
Okay,
yeah,
that's fine. So if you guys remember, so once we loaded once we imported the load current, the BV current, we save it in this var mat file. So now we need to use it in the current flow model, because in the current flow, as I said before, it's a relation between the BV current, the load current, and the battery current. So in the fitness function, once we define the position based on the minimum and the maximum limits, we used that position to test, is the value, for example, less than the threshold or more? Should I move toward down or towards up or right or left? So the thing that will decide is calculating the fitness function. So far, the things that I explained, it's the general, let's say, common thing between all the optimizers. The specific thing for this problem is in the fitness function, which is the current flow. So I'm gonna now just explain the current flow. So the first thing is the output from this function is F total. F total, because we use F as a fitness function, or we can call it objective function, it's up to you. So F total, it's the summation, or what we call it, the weight sum of the first objective, which is loss of load probability, technical impact, and also the economic impact, which is the annual total life cycle cost. Because it's a multi-objective function, so I have two functions. So this is the output that will this function return to the main optimizer to decide, am I moving right? Should I stop here? Should I go down? Should I go right, left? To do like search for other solutions. So what's the input? We have M and N. M and N, what's they stands for? M stands for the number of PV modules, and N is the number of PV of the batteries. So these the two solutions that we're looking for. We're looking to optimize to find the number of PV modules and the number of the batteries. So that will be the input, and this input based on the circle that just I explained. So for example, once we are here and we have a solution in this point, so this solution in this point could be 2 batteries and 1 PV. So this is the input for the fitness function, which is represented by M and N, okay? So I'm gonna use these two into the current flow between the PV battery and the load. And based on that, I will find the F total, give it back to the optimizer to decide, is these numbers are the optimal values, or should I reduce it or increase it, okay? So the first thing here, we define the state of charge of the state of charge of the battery, which is the maximum, which is 1, which is 100%. We represent that as 1. The second state of charge equal to that, which is a temporary value, it equals to 1. So we expecting that the battery, once we installed it, it's a fully charged. So that's why this is a temporary state of charge variable. The second one, the third one, sorry, state of charge 3, it equals to the minimum depth of like the depth of discharge, or the minimum battery state of charge, which is a 20%. So we can't discharge the battery in this case more than 80%. Otherwise, we may damage the battery. The voltage of the battery, it's a 12. As I mentioned before, in this case, we used a battery with a 12 volt. You can use 24, 48, whatever available in the market and based on your project. This charge efficiency is 0.8. As I explained before, the depth of this charge in our case, 0.8, which is 80%. The number of cells per batteries, how many cells? We have 6 batteries based on a 12 volt battery. So dk, those are 2 parameters related to the charging and discharging. T equal 1, which means one solution, T equal 1. At the first time, we're gonna start doing that. The current of the PV equal to M multiplied by the current of the PV. As I explained before, the current that we got from LSTM is for 1 module. So if we need the current for 4 modules, we're gonna multiply that by M if it's connected in series, okay? So the state of charge maximum equal to N, because here we're trying to calculate the state of charge, not the number of battery, and based on the state of charge maximum, we will convert that to find the number of batteries. So this is the equation that we can use it to find the state of charge minimum, okay? So state of charge minimum, it's a state of charge max multiplied by 1 minus 0.8, which is a 20% of the state of charge maximum, okay? Which is should not exceed or goes down less than 0.2, which is a 20%. So as we have several hours, in our case, we used a data for 1 year. So we have 8,760 hours. So that means we're gonna do this optimization per each hour to make sure that our system can meet the load with a high availability, less cost during whole of the year, not just for 1 day, 1 month. We used 1 year data. So the optimization is trying to find the optimal size of the PV and batteries that can meet the load with high availability and low cost during the year. So that will be more accurate and more realistic once we use 1 year data, because like in the summer, the situation will be different than the winter. So the size that we're gonna find in winter, it might not suit in the summer. And the size that we will find in the summer, it might be oversized for the winter. So we have to find a solution that can, balance these two situations. So the first thing is we find current INET, which is the current as a relation between IPV and iLoad. So if IPV is more than iLoad, that means INET will be positive. If IPV less than iLoad, then the INET will be negative, okay? So the second thing is we checking the state of charge maximum. Is it more than 0? So if it's more than 0, then we have if it's more than 0, so that means we have like there is in the battery, like there is a current in the battery, we can use it to discharge the battery. So here the first thing that we check, if INET equals 0. So is the values of the net current between the PV and the load equal 0? If it equals 0, that means all the generated current from the PV went to the load. So we don't have any excess energy. We don't have any excess current to store in the battery. So in that case, iLoad equal IPV because the value is 0. So there is no damping current. Damping current is 0. There is no charging current. Because there is no excess energy or no excess current. There is also no deficit current because they are matched. If iLoad is more than IPV, then there is a deficit. This is charge 0 because, again, there is no deficit current. The load can cover all of the demand from the PV. We don't need anything from the battery. So the same thing, I battery equal to 0, okay? So by doing that, we just make sure that state of charge are still the same. In each case, we have to calculate the state of charge because here we did not did anything. So just we make sure that the state of charge is the same. So the second option, if INET more than 0, so more than 0, that means if we back to that relation, so that means IPV is more than iLoad. So that means I met the load demand and I have excess energy. I have excess current. I need to store it in the battery. If the battery is full, I need to damp to throw this current out. So in this case, iLoad equal IL. State of charge equal state of charge 1 because we did not use the state of charge before. So idamp equal inet, which is the remaining. We may throw it as a damp, or we may save it as an excess in the battery if there is a space, empty space in the battery. Is there any charging? No charging. Why no charging in this case? Because if we back here, we check the first thing, state of charge maximum more than 0. So that means in this case that the state of charge of the battery is full. We can't charge it. So all the current remaining, we're gonna damp it. We're gonna throw it in a damping load, a heating like resistance or resistance. We're gonna just damp this current because we don't need it. It's an excess energy, excess current as well. Any discharge, there is no discharge because I did not discharge the battery. Any I battery, there is no I battery because there is no charging or discharging. So, okay. Okay, so this is for the first time, k equal 1. So what means by k equal 1? So that means for the first iteration, because in the first iteration, the state of charge of the battery is full for the first hour. If I go to the second hour, which is k equal 1, in this case, I may need to charge or discharge based on the second current in the second hour. Like what's the output or the load current in the second hour? Okay, so here we check that state of charge equals state of charge 1. So I damp equal to the I net. Okay, in this case, still we don't have any charging or discharging. If state of charge is less, so that means the state of charge now is less than 100, let's say 0.90 percentage. In this case, I can charge. So this is how I'm going to charge. So the I net multiplied by 20.1754, which is the parameters I just explained before, K and D. And these just for the like some of the losses, just to make sure that the charging current is accurate. Okay. So once the state of charge of the battery is less than 100%, then now I have a place, an empty place in the battery. I can start to store the current inside it. So in that case, there is no damping current, and all of the excess current will go to the battery. So in the charging mode, I have to calculate the voltage and also the resistance to calculate the state of charge again, because 90% it was before. So once I added a little bit of current to the battery, it might reach 100% or it might reach 95%. So I have to use the voltage of the battery, resistance of the battery to calculate the new state of charge. The third case, if the current of the PV less than the current of the load, in that case, we need to get a current from the battery to meet the load current. So that's what we did. We check here, and again, as we're gonna see here, we don't have any charging. We don't have any damping. We may have deficit if the battery is empty. So we're gonna firstly consider that the battery is not empty. We're gonna discharge the battery with that amount of current, okay, to meet the load current. So in this discharging mode, we have to do again calculating the voltage, the resistance inside the battery to calculate the state of charge to make sure that still we have some energy inside the battery that we can use it for the next hour. So here we have every time we do charging, discharging, or in any state of the calculation, we have to make sure what exactly the state of charge of the battery. Is it full? Is it empty? Or we have some energy stored in the battery and how much that energy. So once we did that, we again going to check the state of charge of the battery. If the state of charge of the battery is still more than 20%, then yes, I can do discharge. I can discharge now the battery to meet the load demand. Okay. If the state of charge of the battery, the current one, is equal to 0.2, 20%, that means I can't discharge the battery more. In this case, as we can see, we don't have any charging, discharging. We have something new called deficit energy, deficit current or energy. The deficit current in this case, that both PV and battery couldn't meet the load. So this deficit current, we're gonna use it to calculate the first objective function, which is the loss of load probability. So again, some of the same cases to make sure that we did not did any mistake before. Because of all of these equations and comparison, we want to make sure that at every time step, this is just to double check that the calculation that we did before, they were right, okay? It's just to double check. So once we found the deficit current, once the PV and the battery couldn't meet the load, we can use the equation which equal to the summation of the I deficit over the summation of the accurate load or the current load, the actual load. So by applying this relation, we're gonna find the loss of load probability. So our idea or our aim to try to reduce LLB as much as I can. That means reduce the times that the PV and battery couldn't meet the load, okay? So this is, we call it F1, which is the first objective function. So here we found the maximum because at each time step, we need to find the value. So like it could be like this one is the once we say maximum, so that means it's just like a name. Actually, it's a typo error. It should be minimum, but here we're trying to find the same relations to find the minimum value. So if one here, it could be 0.2 at this iteration, but for the next iteration, it could be 0.3. So we need to keep the 0.2 as the threshold. In the third iteration, it could be 0.19. So we need to take that, keep it in the memory, and start compare the new solution with that value. So that's if statement doing that, okay? So this is the first objective function, which is the loss of load probability. The second objective function is the annual total life cycle cost. For the annual total life cycle cost, that contains the capital cost for the batteries, BVs, inverter, converters, or the charge controllers, protection devices. Also, it contains the maintenance cost for the BV, the battery, and all the devices. It has also the replacement cost for the batteries. So these are the costs for all of the components for that BV system or standalone BV system. All of these components, we took them from the market. So every time and for each battery, HPV, these values could be changed. So you can change it based on your case. So once we defined all of these costs, we know now the size of the battery and the size of the BV that we used, which is M and N from the first of the code, M and N, which is the initial position the optimizer defined for us. So based on that, we're gonna calculate the annual total life cycle cost. So these equations to calculate the annual total life cycle cost as a relation between the component prices that we defined here and the size of the BV and the battery. So that we called it F2, which is the second objective function. And we did the same thing here because each iteration, this value could be changed. We need to keep the minimum value for us, okay? So once we have the first objective function and the second objective function, because this is a multi-objective function optimization problem, so we have to find a relation to contain these two functions together in one value. So that's why we used one of the ways. It's called weighted sum multi-objective function. So it's the weight multiplied by the objective function over the maximum value for that function, okay? So that's why we call that as a maximum, because we want to find the maximum value, okay? So again, so this one, we can use it for two reasons. The first one, to make sure that the function that we have is the minimum, and also to find the maximum value that we needed in the weighted sum multi-objective function. So because the technical aspect is more important for us than the economical aspect, so that's why we gave a weight for the first objective function 80%, and for the second objective function, the economical one, 20%. You may change that based on your interest and based on the problem. You may make it 50-50, 60-30, 60-40, but they have to be 100 or 1 as a summation. So based on that, we found the F total, which the value that represents the value for the both function that we have, loss load probability, and the annual total life cycle cost. Is there any question for the current flow or the objective function before I back to the main code? Any question? Okay. So based on the objective.
Excuse me. Hello.
Yeah.
Yeah. When you are describing about battery is full charged and your load current is also, there is no change in the load current, you're saying that the excess amount of current is going to dissipate, right?
Once you mean the battery is fully charged and there is more current from the BV, we're gonna damp the current in that.
Okay.
So just a
damping
small thing. Yeah, just a small clarification. We're gonna damp it in this option once we have, for example, 2 batteries. But when we have 3 batteries, we may charge it in the third one. So that's why we try different options.
Oh, okay.
Yeah.
So you are making as a spare.
That's the very worst case. I mean, situation, and in most of the cases, I mean, we try to avoid that situation. Is that right, Ibrahim?
right. If there is a high damping current, that means the PV is oversized.
Right. Okay.
We don't need to have high damping current. At the same time, we don't need to have high deficit current, like the PV and the load and the battery couldn't meet the load. So that's why we try different options. So all of that explanation for one option, that this is the first initial option. We're gonna try this thing 500 times. Every time the optimization technique will change the number of PV, number of batteries, and do this calculation again. So 500 times we will repeat this process until we find the optimal size. Optimal size, that means lower damp current, lower deficit current, lower cost. So lower damp, lower deficit means lower loss of load probability.
Okay, perfect. Thank you. Thanks.
Any other question or comments? Or, I mean, do you understand, or you find like, very difficult to follow? I know, I mean, if someone does not have any background with MATLAB or, power system, might be difficult to follow. But I mean, Ibrahim is trying to go, and also as detailed as possible.
Looks good, sir.
Yeah.
Looks good, sir.
Okay, that's okay.
Do you still have time, or just maybe
Yeah.
5 minutes?
Yeah, I still have what time? Yeah, continue.
Okay. So all of that process, as I mentioned, we're gonna do it 500 times. Each time, the output, which is the F total I got, it will return to the main optimization technique as an objective function. And then here, this type or this piece of code here, we will decide, is that the minimum value, or we may have less value than that. If it's the minimum value, if I back to the paint here, the minimum value, for example, if I'm here in this area and I'm just close to this solution, so this is the minimum value. If it's the minimum value, then the MATLAB every time to just search 500 times, it will give us the same size of that battery or and the PV. If it's not the minimum value, let's say we are here in this area, then it will give us a new option, a new number of PV, a new number of batteries, and do the same calculation of the current flow again to give us again the value of the F total. So that's what exactly here. Here, this piece of code, just make sure, is that, this one here, is that the minimum value or not? If it's the minimum value, then the global solution will be the initial position, or the position that we defined before. The position here, as I mentioned, it means a number of PV, a number of battery. Okay? So then we do some sorting to rank these solutions, because every time we have solution, we need all of the solutions to draw the performance of our optimizer. It started with high objective function and then start decreasing until it reached the minimum value of the objective function that giving us the optimal solution. So after we decided if it's a minimum or not, we do again some sorting, and we save that in the keep global matrix. And from that, we have something called nbest. If we see it's x1 and 2, which contains two values, number of PV, number of batteries. For each objective function value, we have two options giving us that value. For example, 5 batteries, 10 PVs, giving us 0.2. 6 batteries, 20 PVs, giving us 0.1, for example. So we have to keep this option, these two values, with the minimum objective value that we got. Then at the end, we will decide which one is the better for us. So all of that process that I explained, it was just for the initial value. So now here, we're gonna start again doing the same process from iteration 1 goes down to iteration 500. So all of that code, I'll go through it very quickly because it's the same explanation as before. For example, if we back to this one here, and we found that this solution is not the accurate, we need to go in this direction, okay? So in that case, we need to change the position from this point to this point. We need another point here. So changing the position and the velocity of the jumping from this position to this position, it will done here. So here we change the velocity, and again we change the position. Okay, changing the velocity, the position for the new point to search is the objective function is lower than the previous one or not. So once we get a new velocity, a new position, we're gonna do again to check the objective function. We will take this value, go down to the fitness function, do the same calculation, give us the same value. Okay, so each time, as I mentioned, one of the good thing with this optimizer, it has an internal optimizer, built-in optimizer inside it, that doing an optimization for the hyperparameter for itself. For each iteration, that hyperparameters for the wind-driven optimization, it keep updating to give us the best option, the best solution. So the same thing to find after we change the position, the velocity, and we calculated the fitness function, we minimize it, make sure is it minimized or not. How we gonna check that? We're gonna check that from here. We called it updating the global best. Is the minimum pressure that we found less than the global pressure? So the global pressure we calculated in the initial solution, the initial position. The minimum pressure we calculated once we update the position and the velocity. If the minimum is less, that means the new global equals to the minimum. Okay, and if in best equal to if best, which is the new solution for the number of PV, number of batteries. So here we keep that global pressure as a matrix for all of the solutions. And then here we find the best PV and battery best, which is the best number of PV, the best capacity of the battery, and we display that. We show that. So if we just back to the paper, just to match these things with that. Yeah, here. So do you see here? That's what I mentioned by 500 iteration. As we can see, start from 1 to 500. So the initial solution was here. So that means the objective function at that point, it was, let's say, 5,200, for example. It's still not the minimum. For the second iteration, we can see it start dropping because we're decreasing here the annual total life cycle cost. And it's already decreased the loss of load probability. So all of the solution here equal or less than 0.1. So that's why we just show the annual total life cycle cost. For the second iteration, third iteration, as we can see, it started dropping for different options until we, for example, reached 12 or let's say 11 iterations. This is the minimum value if we're back to the here. So now the optimizer found the optimal solution and it's still keeping looking here. So that's why it couldn't find any minimum value and it keep giving us the same value. So that means it converged and giving us the value. So this is an example of the annual total life cycle cost. I'm just gonna give you a very quick thing. So this is the output that we will see from the code, the size of the battery, and also the capacity of the battery. In the code, actually, it will give you as a number, let's say 6 or 12 BV systems and 2 batteries, for example, okay? So that's all from my side. If any question there, let me know. Anyone have any question?
Sir, the convergence plot that you showed a moment ago, the y-axis was the objective function, right?
The y-axis was the objective function. So actually the y-axis is objective function. That's right. Is one of the objective functions.
Okay.
But all of the values in this blue, they satisfied the first objective function, which is 0.1 loss of load probability.
Okay.
Yeah.
Okay.
Any other question? Yeah.
Sir, I don't understand why the algorithm that you propose is working better than PSO or the other methods that you considered.
So more than one thing. The first thing is, if you remember, I explained, I show you a small thing here in the code. Let me just go for it. Yeah. So we use an internal optimizer inside that. So BSO, it has hyperparameters, and these hyperparameters, they are not optimal for this problem.
Okay.
But the multi-objective model-driven optimization, at each iteration, it's changing the inside the internal hyperparameters to increase, to improve the output. So that's why it's giving us better results than the other algorithms. It's, as you can see, there's a somehow big difference, and it's even faster than them because of that optimization.
Okay.
Yeah, yeah.
Okay. Got it.
Any other question? All good? Doctor, I think you are muted. Sorry.
Sorry, I mean, if there is no other question, thanks, Ibrahim,
No worries.
for your, I think, very detailed discussion. I hope that is useful for all the participants. Basically, if someone is interested to apply multi-objective optimization for, I mean, it could be for any application, although, I mean, you have shown for sizing battery and photovoltaic system, but it can be applied to many other applications.
That's right. Yeah. So thank you very much. Thank you for your time, and hopefully that you enjoyed the lecture. If you have any question, I believe you have my email address. I'm more than happy to answer any question. Thank you very much, and enjoy the remaining of the session.
Thanks, Ibrahim. So I'll just give you like 3 minutes break, 3-4 minutes break, and then we'll start.
By that time, can Samir, you introduce yourself?
Anyone from here is working on like that optimization, I mean, or application optimization?
Sumit, what was the issue with the link?
Sorry?
No, Sumit had some issues with the link.
Okay. Hi, Altab. Can you hear me?
So you're audible.
Okay, you can also see my screen, right?
Yeah,
Yes,
it's
sir.
visible.
Yes, sir.
Okay, thanks for confirmation. So for the next half an hour, we have got around 30 minutes. So next and half an hour, I'll show one or two application for electric vehicles. So probably if you can remember that before starting photovoltaic system, we discuss electric vehicles, and I show the electric vehicle car charging system, and then I just show one application for electric motor drives. That was mainly a robust control to minimize the effect of temperature change, which also changes the resistance, and that's how it has got some impact on the EV motor, speed as well as torque performance. Now the next application I'm going to show, this is a fault tolerant option for again induction motor drives. For that could be for any application, but here we just targeted for EV application. So you might know that the fault tolerant control concept that is getting popular in recent years because as you know that we always expect maximum reliability for any devices. So we expect that they would be connected and continue to provide service even there is a fault. So fault, as you know that if you have any devices, the fault could be either internal fault or even the fault could be external fault as well. So for example, if you think about a electric motor drives, it has got inverter converters, and those inverter converters, they have got their internal like switches inside. So it could be that there might be some short circuit fault inside, or it could be some switch failure, or it could be some, due to switch failure, it might be even like an open circuit fault as well. So this is just giving some statistics about what type of fault happens in the system. So it says switch failures about 40%, mechanical fault around 25%, from externally grid side it could be 20%, and supply failure is 15%. So any cases, the fault have negative impact on the performance of any system. So if you can have a fault tolerant control, that would be applied to address these challenges. Now here again, as I say, we mainly targeted here open circuit fault as well as short circuit fault. So the voltage sensing method, and that could be utilized to detect short circuit fault. And the open circuit detection could be like a normalized DC current method. But there are many other methods as well. You could also have you could design some observer which constantly monitor the voltage and current, and for any devices, and here for electric vehicles, so you know what's the normal current and voltage for its normal operation. So if you see there is a exponential or heavy changes in voltage and current, so that means you can say that there is a something wrong in the system. So just by comparison, this normal value and abnormal value, you can easily identify there is a fault, but what sort of fault, that also you can identify from voltage and current, either is short circuit or open circuit. So that's why here we just mentioned, like, initially just identify open or short circuit fault. If there's a yes, then we have to identify what's the fault location. That means, identification of faulty switch or leg. And then, we have to diagnose the fault. That means, here, initially we just, propose like that in a redundant leg for the inverter. And that's how actually you can again return back to the normal operation. But while you, here important things is that how accurately you can identify the fault, and then how you can diagnose and how your control going from faulted to normal operation. So you have to make sure that whatever the operation it has got before the fault and the performance that you are getting, your control should provide the similar performance during post-fall condition as well. Now here, this is the very simple concept that in the normal converter you will find this 3-leg, and here again this is like a impedance source based inverter, and here just to make it fault tolerant you have got another redundant leg with that one. And here also, you have got isolating thyristor as well as inserting thyristor. Now what happens, when there is a fault, like this inserting, this isolating thyristor will actually, if there, for example, if there is a fault in this leg, it will disconnect that particular leg, and this inserting thyristor, from the control, it will recognize that there is a problem in the system, and then it will connect that redundant leg with this particular leg. So that's why if any of this fault happen in any of this leg, so this redundant leg could be come into the operation by using the operation of this isolating thyristor as well as inserting thyristor. But at normal operation, this does not have any impact. This is off. So you'll get the normal operation from that system. So again, I already talked about this mathematical model, and here this is for like this system. And again, I'm not going to talk variable by variable for this induction motor drives and any question. And this is also quite standard for induction motor drives, that where you are having your sensing speed, and as well as that rotor position theta, and also you are getting current for here. So this voltage and current sensor, you are measuring this, sorry, here speed and your current sensor. So the speed is coming here, and then this 3-phase current that you are measuring, again same we are converting to DQ frame, and then comparing with this measured and reference value. At the end, you are getting that signal which is coming to your PWM, and then it's coming to your inverter. So that's why this is quite standard for any induction motor controls. And that concept here, we applied in our lab as well, using machine power supply inverter, then your impedance source network, as well as using displays board and voltage and current source sensor. And here, what you can see in the very top figure, this is again, without using fault tolerant control. And here you can say this is like the normal operation. I can see it's like a pure sine wave. There is no problem with the output current and voltage. Now, the next one is like a open circuit fault, and you can see that even like if there is a like in one of the leg is have like open circuit, but you can also see like because it's one half of this is open, so you can see that it's still it also affect the operation in other phases as well. So it's quite distorted. It's not pure sinusoidal, and same for like short circuit fault as well. And here also you can see that it also like affects the output current, shape as well as the power quality significantly. So that's why if you have that's like the normal control, and if something happened, it will main gate as well. Can you hear still? Can you someone confirm if you can still hear me? Okay.
No, sir.
Yes, sir. Yes, sir.
Okay, thank you. And the application that here we considers, that's a shopping mall, which was like very close to my previous university. It's called like Macquarie University Shopping Center. And while we designed that charging system, we also considered the constant that you have in the grid, and also the transformer constants as well. And this is like the conceptual architecture for this parking lot. So here in the left hand side, you have got AC bus, which is nothing but like your main supply. And then you have got a transformer, which is again connected with your the converter. And here is a switch. If you like to control like the grid, whether in case if you want to make it off grid, you can use this control switch. And then you have got DC bus. This one actually converting from AC to DC. Then you also have got here in the DC bus the battery energy storage system. And as I mentioned, that we want to find that optimal sizing for that particular parking lot. And we have got on-site photovoltaic system, which is also connected with a DC to DC converter to the DC bus. And then that's your EV charging point. And here also, I mean, you have got control switches. So if the parking operator, I mean, they can also use that switch just to control charging for, I mean, different vehicle. And this like DC to DC converter that also control the rate of charging for different vehicle which is connected with this, I mean, DC bus. Now again, I mean, here the research challenge is, I mean, how we can find what's the demand profile for that in a particular parking lot, because I mean, I would say, like, it is a parking lot. Every time vehicle is, coming, going, it is also not sure how long the vehicle owner, I mean, will, stay in that particular shopping mall. What was their, like, initial SOC when they're leaving? I mean, what's their SOC? And when they're, like, staying there, whether, I mean, they are, I mean, also interested to participate in the V2X services as well. Now, also, like, you might know that in many countries now, this shopping mall, they are also thinking to give like free charging for the vehicle owner, but the condition is that they can charge their battery freely, but while they are in the shopping center, if there is a need, I mean, they should allow to participate in the V2X services. And if you give that, like, incentive, many vehicle owner might be interested to participate in that V2X services. Now the data that, I mean, we collected, like, that vehicle data from that shopping center. So here we found that this is like one of the very biggest shopping center in that particular area. So we found that on an average, like, 17,000 vehicle visited that shopping center per day, because there are also many industry, many, like, even in university, and most of the university, they have got main their offices in that particular area as well. And here also, I mean, from the data that we found that, like, more than like a 23% of vehicle, they park there just like, for might be like 30 minutes, less than 30 minutes, and then or 1 hour, and then 75% like up to 2 years, and then almost 90% like, departed within 3 hours. And while we are characterize the EV demand, we consider mainly the 5 parameters here, like the arrival time, departure time, battery capacity, and then the rate of charge for the battery, and then the mainly on an average, like, total kilometer travel by that particular vehicle. So that's, I mean, I already mentioned that these are the things, I mean, we consider. So I mean, another factor also, I mean, we try to consider this driver behavior and also that weather condition, because we found that, I mean, the driver behavior and also the road condition, that's also have, like, significant impact on the battery capacity and SOC that used, I mean, by the battery when they are driving. And some of the factors, I mean, here already given. So it's more like, it's like a daily distance travel, 87% vehicle, like 35 kilometer per day. That's we found. And here in the shopping center, initially we just consider like level 1 and level 2 charging. And this is the, mathematical model that we use for the parameters that I mentioned. And here we have considered a probabilistic distribution function just to model the load demand, because as you know, there are so many uncertainty here. So using like a direct model, it's quite difficult. So that's why probably it is recommended that it's better to use the probability model, because there are so many uncertainty involved here. And then we use that, logarithmic normal distribution for arrival and departure, time modeling. And here you can see that's the top figure. The blue one that shows like the departure, and other color that shows like the departure time. And you see like that percentage of vehicle that's there in the shopping center. The next one, distance travel by EV. We found that characteristics, and then the energy consumed per kilometer, kilowatt hour per kilometer. And this is the equation that we can use to just find the energy. So this is the battery capacity, and if the kilometer is maximum, then that would be the capacity. But if they less than that, otherwise, you have to multiply like the distance travel as well as the per kilometer energy they need. And then you can also find out the charging time and the load demand, and then this is like the total payload for that particular shopping center. And you can see here like there are like two variables here. One like in a standard deviation, and another is like a mean deviation. And then from that one, for that particular application, these are the value that we got for that particular shopping center. So another lesson, we learned from that as well, that's due to that driving style, the energy consumption of the PV actually varies up to 33% of its rated value. And better capacity could be degraded up to 11% of its rated capacity. And as I also mentioned that almost 90% of the vehicle, they travel less than 45 kilometers per day. We also find that for that particular shopping center, most of the people, they live like within 5 to 30 kilometers distance from their homes to that particular shopping center. And again, this was the arrival and departure SOC for the vehicle that actually departs different time of the day. And considering that particular location and radiation level, we found that these are the PV output that can be found for that like an on-site PV. And then our final target was to find that battery capacity considering all the grid constant. So here again, for like the optimization, I haven't shown all the equation because Ibrahim has already given like a detailed description of that. So what we did here for that one, that we have got input as temperature as well as radiation for the solar, which is used to estimate the solar output you can get from the on-site generation. And then we use like that, Monte Carlo simulation just to approximate that, and then we use that stochastic probabilistic modeling just to find the EV charging load demand. And as I mentioned, these are the input for that particular modeling. The arrival at departure time, distance, driver behaviors, battery capacity, and rate of charging. So we did consider the battery efficiency as well. And here, that's actually overall algorithm that we have used to find the final battery capacity. So again, this is quite not exactly same, but quite similar what Ibrahim mentioned. So I'm not going to repeat that one. And again, that was the result that we find from our case. So the initially, here, if we don't optimize that system, if we just randomly use, we found that some part of the day it actually exceed the capacity of that grid. But here, while we have got that optimized better with the system, it remains within the particular it satisfies all the grid constant in terms of transformer capacity, like the cable capacity, and at the same time, it also can satisfy the EV charging demand as well. And we just consider different option, like if we use less battery capacity, you need more power from the grid. So that's could be like a trade-off. If you'd like to also, optimize the overall cost, but here, we didn't optimize the overall cost. If you want to optimize the overall cost, then probably we also could find out what percentage power probably should get it from the main grid. What could be that PV capacity, and what could be that battery capacity. But here we just consider that standard PV, and then we just consider different option from the grid, and corresponding to that we just consider the battery. We determine the battery capacity that we need. Okay, so probably I'll leave it here for today. But these two applications that I mentioned, if you have got any question or comments, feel free to share with us.
Right. Vehicles are going out. The SOC is 100%. Is that possible?
Well, as I mentioned, if they when they're coming, in the shopping center, they are charging on the battery. So, when they come, if they have got initial SOC a good level, and the time they stay, it might be possible that when they are leaving, they have got maximum SOC. But again, it depends on what's the limit that you have choose. If you charge up to maximum 80%, then it will not cross that limit. But here, we did not put that constant. That's why it goes
Okay.
yeah, that's the maximum limit that you will be choosing, that will go up to that particular level, SOC level.
Sir, where we can find this EV data, sir?
That's a good question. I think what I heard that in USA, so you want charging and discharging data? I
Yes,
know
sir.
some of the open source data that's already available.
How to model the EV load?
Well,
you have modeled using some probability distribution functions. So for that, it's required, historical data is required. So
that's right. In that case, as I said, those sort of data is very difficult to find. But what you can do, I mean, the area that, I mean, you are living, even if you consider like, just like consider that normal vehicle, right? And just get like, you know, their like, you know, arrival time, departure time, and then like consider on an average, like, you know, how many kilometers they travel, and then just like using some standard you know, charging discharging profile, because it's also possible to I mean, relate the charging discharging profile with the distance travel as well. So that's how probably, you know, you can even utilize those, I mean, open source charging discharging data with the, like, you know, particular area that, I mean, you would like to make the modeling. Although, I mean, it wouldn't be like, you know, 100% accurate, but I think still that might be a good starting point, because so far, I mean, I understand like that we don't have that many vehicles, and also like in a shopping center, we might not have the charging infrastructure already built as well. And even like in a somewhere is built, I mean, it's not easy to get, I mean, all the data. I mean, charging discharging, that's possible to get it.
Sir, can you tell us like where we can get?
Well, I mean, if you just send me an email, I mean, I'll give you some link that's
Okay.
already available.
Sure,
But
sir.
I cannot remember the name of the whole link, but I mean, I'll give you the link.
Okay, sure, sir. Thank you so much, sir.
Yeah, you just send me one email, and yeah, I'll give it to you.
Today I saw the news that American government gave $6 billion to this charging network.
Yeah, I mean, that's definitely a good news, and I believe, I mean, that's will happen. It's just a matter of time, and hope, like, you know, once you have got those infrastructure, you can easily get data from the local sources as well. Anyway, if there is no question, Altaf, I'll leave it here. Thanks everyone. Have a nice weekend, and I'll see you next week.
Thank you, sir.
Okay,
Thank you,
bye.
sir.
Thank you.
Thank you.
Sorry, I missed it out. Tomorrow the session is from 2 p.m., not 1 p.m. And have the first session from Professor Saidulo. Then next I'll be conducting on renewable energy costing. It may be a long session. Actually, I didn't want to take sessions on weekdays. Otherwise, we'll have to continue it with after 1 to 3.